In this second video of this multi-video mini course, I introduce Lewis electron-dot structures as the first of 5 key elements or skills that you, the beginning student of organic chemistry, should have mastered before the first day of your undergraduate class in organic chemistry. On this slide, I show the Lewis electron-dot structures of 5 simple molecules going from the upper left in a clockwise direction. Around the slide, we see methane, CH4, we see ammonia, NH3, we see ethane, C2H6, we see ethylene, C2H4, and we see carbon monoxide, CO. What you immediately see from this depiction is that a line is equal to a pair of dots, indicating or representing one pair of shared valence electrons constituting a single covalent bonding interaction between 2 neighboring atoms. You can also see in the structures of ethylene and carbon monoxide that both double and triple covalent bonds are possible. You can see in the structure of ammonia that some structures involve what are called lone pairs of electrons. Localized on nitrogen, these are non-bonding valence electrons that come with the atom, so to speak, as the atom forms bonds to make the molecule, but they aren't part of the bonding system. Nevertheless, it's very important to recognize and to clearly show these lone pairs when they are present. On this slide, you see the same 5 molecules with the same 5 Lewis electron-dot structures, except now you see the electron count, and the counting is the octet rule. So in fact, when your professor asks you to represent or sketch a complete and valid Lewis electron-dot structure given a formula, then what they're referring to is this count to satisfy the octet rule. Remember, the octet rule for all elements except hydrogen, of course, is 8, as the element in its bonding mimics the S2P6 8-electron closed shell configuration of the noble gas elements in group 8A or 18. Now for hydrogen, the nearest noble gas is helium, and helium has only 2 electrons. So the octet rule for hydrogen is really a duet rule. And so you can see for methane that the count for carbon is as follows. 4 carbon-hydrogen bonds times 2 electrons per carbon-hydrogen bond is 8 electrons. In other words, carbon in the molecule feels 8 electrons and feels like neon, where hydrogen has only 1 bond, and it gets 2 electrons for that 1 bond, and it feels like helium with 2 electrons. Now notice something here. We intentionally double count the 2 dots for both elements. That's intentional, and without going into a long justification for why that's so, a quantum mechanical explanation, take my word for it, it's the way it's done. Moving on to ammonia, the difference between methane and ammonia is we have what's called a lone pair. And a lone pair is a pair of valence electrons for an element, and nitrogen and other members of group 5A, and oxygen and group 6A, and fluorine and group 7A often show 1 or more pairs of these double dots localized on the element called lone pairs. These are valence electrons that come with the element or with the atom, but aren't involved in the bonding. But it's still very important to show them because their presence or absence can dominate the predicted chemistry or behavior of that molecule. What else do we see in this slide? We see the possibility of double and triple bonds and how these are counted. So for instance, for ethylene, the count for carbon is 2 carbon-hydrogen bonds plus 1 carbon-carbon double bond, which is worth 4 electrons for a total of, again, 8 electrons. For carbon monoxide, we see 1 carbon-oxygen triple bond worth 6 electrons and a lone pair, again, for a total of 8. One more point here, which is that for carbon monoxide, you cannot write a valid and complete Lewis electron-dot structure and satisfy the octet rule unless we invoke what are called formal charges. And you can see that the charge on carbon is -1 and the charge on oxygen is +1. Remember, carbon has 4 valence electrons, but in this Lewis structure, 3 of them are being used for the triple bond, and the lone pair are electrons 4 and 5. Hence, carbon shows 5 associated electrons in the molecule, and it must have an extra electron, hence the charge of -1. Oxygen has 6 valence electrons. It's using 3 for the triple bond and shows 1 lone pair, also for a total of 5. But because oxygen has 6 valence electrons, we show a formal charge of +1 for the 6th missing electron. So the counting for formal charge and the counting for the octet rule are very different. The counting for the octet rule is intentional double counting of the 2 dots or line, and the counting for formal charge is localized relative to the valence electron count of that element and the contribution that the atom or element makes to the bonding using those valence electrons. Okay, so now that you've seen some examples of Lewis electron-dot structures and how the counting works, what I need to teach you is how to generate a valid and complete Lewis electron-dot structure given a molecular formula. And so, of course, molecules are made up of elements or atoms, and the atoms form bonds, in this case covalent bonds. And so if you're to master Lewis electron-dot structures, you need to first understand how the dot system works for the elements themselves. So let's take a look at the periodic table of the elements and remember that the groups, which are the columns, can be numbered in one of 2 ways. They can be numbered from column 1 all the way going to the right through and including column 18. Right from hydrogen all the way over to helium. Okay, that's the modern numbering system. The more traditional numbering system uses the A and B notation, where the main group elements are the first 2 groups, 1A and 2A, and the last 6 groups, which are 3A through 8A, or in the modern system, 13 through 18. And all the B elements are in the middle, and these are the transition elements. The octet rule applies only to main group elements. It does not apply to transition metal elements. And so all the Lewis structures that we will be working with and looking at will involve, at least for now, main group elements only that must satisfy the octet rule. And so this is how the dot system works for the main group elements. And so you can see that according to the traditional numbering system, 1A, 2A, 3A through 8A, which is what you see on this slide, the Roman numerals correspond to the number of valence electrons. And the system is this. Imagine that each element or elemental symbol has 4 corners. What we do is we put a single dot or valence electron in each of the 4 corners, as we have valence electrons until we have 4 single dots in all 4 corners. This happens with carbon and its friends in group 4A. Then as we proceed from carbon to nitrogen's group, and to oxygen's group, and to fluorine's group, and we add 1 valence electron each time we move to the right, we start doubling up the dots. This slide shows that where we double the dots doesn't matter. Okay, whether we put the double dot for nitrogen on the top corner or in the left-hand corner or on the bottom corner makes no difference in how we're going to eventually use nitrogen, right, to form a molecular structure. However, that 4th example on the right with the sad face, no, that's not kosher. And because it violates, again, the rule that we have to first have 4 individual dots in all 4 corners before we start doubling up. In this last slide for this video, I show the Lewis electron-dot structures of 2 very real and very common and important compounds. The first is sulfuric acid, which has the formula H2SO4. The second below that is phosphoric acid, which has the formula H3PO4. Now, what I want you to focus on is the electron count for the central atoms, sulfur and phosphorus. You can see that in the Lewis electron-dot structure of sulfuric acid, sulfur forms 6 total bonds. 6 total covalent bonds means 12 electrons that sulfur feels in that molecular structure. Phosphorus forms 5 bonds and feels 10 electrons. Now, how is this possible? And doesn't this violate the octet rule? Well, you need to appreciate that once you hit the third row of the periodic table, and sulfur and phosphorus are third row elements, if you remember your quantum numbers and your selection rules and what's allowed and disallowed by the Schrodinger equation, once you hit n equals 3, you have the possibility of d orbitals, where L is equal to 2. L, the second quantum number, right, can vary from 0 all the way up to n minus 1. Well, if n equals 3 for the third row, 3 minus 1 is 2, and L equals 2 is a d orbital. Now, the d orbitals for these elements in the third row are empty. They don't fill until you hit the first transition series in the fourth row of the periodic table, right, with scandium as the first transition element. However, the d orbitals are there. They are available. And so what these elements can do in the third row and below is they can use their d orbitals to make more bonds than an 8 electron count. And they do this to form a wider variety of molecules involving elements of the second row that do not have d orbitals and must obey the octet rule. So in other words, the take-home message here is that for elements in the third row and beyond, these elements can expand their octets. And they do that by using available, empty, but available d orbitals. Okay, well, sorry, this is the last slide in this particular video installment. And so I show the molecule boron trifluoride. Now, boron trifluoride, BF3, is a real molecule. And even though boron is a metalloid, in other words, it's not actually a non-metal, and so a pure covalent bond, of course, is between two non-metal atoms. Boron has plenty of non-metallic character, and so we can certainly characterize the boron-fluorine bonds as largely being covalent. Now, what's unusual about the Lewis electron-dot structure for BF3 is that, unlike sulfuric acid and phosphoric acid, boron has a deficiency of electrons in its molecular structure. In fact, it has 6 electrons, right? So it's 2 electrons shy of an octet. But this is the best boron can do. All elements want to make bonds and form molecules. It is energetically favorable for them to do so rather than existing as the raw element. However, boron is in group 3A, and all the elements in group 3A, boron, aluminum, gallium, indium, right, have 3 valence electrons. And so the best boron can ever do is make 3 bonds. And so boron in its compounds is another octet exception. It's an electron deficient octet exception. And one more thing to note is that these compounds, right, BX3, whether it's a borane, BH3, or boron trifluoride, or boron trichloride, these compounds, while they exist, are extremely reactive, and almost their entire chemistry has to do with combining with oxygen, nitrogen, sulfur. These are atoms that have lone pairs that can then donate both electrons of their lone pairs and form a 4th bond to boron to complete its octet in what's called a dative covalent bond. And a dative covalent bond is when both electrons in a shared pair come from the same atom.